So on the handout that you guys were working with, I asked you to start out with these 3 little toothpicks. And this is originally what we were going to do, is start out with toothpicks and give you guys toothpicks. I don't know, I decided just to do it on paper. I felt like messing around with toothpicks. I mean, I need to bring in like thousands and thousands of toothpicks for you guys to even get a few levels. So, I don't know, did it work out okay doing it on paper? Are you still getting the same idea?
Yeah.
All right. So the idea is that each one of these toothpicks kind of spawns another toothpick, or 2 more toothpicks, and 2 spawn 2 more, etc. And after a while, it gets pretty intense here. Well, commendably, Genevieve, I think you got down to what, the 7th row? 7th row? Or did you make progress on the 8th too? I mean,
did not make it to the 8th.
all right, 7th. That's pretty, pretty determined to get down to the 7th row. That's off to that. I didn't think anyone was going to get past 6, so good on you. But the idea that I was looking for you to do is to start understanding exponential functions. And the fact that these get to be some pretty big numbers really fast is one of the characteristics of an exponential function. Now, what you could have noticed is that you started out with, on n equals 1, we had 3. And then to move down to the next row, you're multiplying by 2. And then you multiply by 2 again. And then you multiply by 2 yet again. And where you start to see the light in terms of this formula is not by continuing to multiply it by 2 necessarily like this, but to realize that that's, say, 3 times 2 to the 4th, or 3 times 2 to the 3rd, or 3 times 2 to the 2nd. And then in general, when you start lining these up, you'll see that, oh, well, this exponent is always just 1 minus that. So the general formula for us in this exercise is f of n is 3 times 2 to the n minus 1. Now it's this part right here that gives you the explosive growth in the number of toothpicks that you would need to complete this challenge. And something like this is an exponential function. Exponential functions are everywhere, and in some good places too. You'll see exponential functions. Well, let me grab this over here. You'll see exponential functions in calculating interest on your bank account. That's a good place. In fact, a nice quote from Einstein is one of the most powerful forces in the universe is compound interest. So, cool on that. Another place you'll see exponential functions. This one's kind of cool. Where is it? Not that one. Here we go. Yeah, this guy. So what happens, what do you call it when a video all of a sudden starts getting a lot of views?
Going viral.
Yeah, it goes viral. Your viral videos are really videos that experience exponential growth in terms of the number of views. So 2 friends tell 2 other friends, and they tell 2 friends, and so on, and it just explodes. This guy's great. He's really good. So I don't think I'd want to clean up the board when he's done with it, but in any case, so the number of views that you get on a video can be an exponential function. You get exponential growth. So, wow, good on you. All right, you got to put that away.
Turned 20.
YouTube turned 20?
Yes.
Wow.
On Valentine's
Are you
Day.
guys older than YouTube or not?
Yes. Yes.
No? Some of you? All right, so you're pretty close. I know for me, yeah, all right, that's...
3 years.
Were you even
I'm
in college
3 years
still
older than
when?
you two.
No, I was well past college when YouTube came out. I was actually already working here. All right, so we're going to work with these exponential functions. Now, just to finish you up here with a little bit of this on the back, you should have ended up with some of these answers. So, the 4th and 5th row, those are pretty easy. There's your general function. If you answered that you're going to go down to the bottom of this sheet filling out this little branching tree, you would have needed about 12.6 million toothpicks or 12.6 million lines just to do that bottom row. So, not to mention all the ones ahead of it. Yikes. At the 10th level, The 10th level would require a little bit more than 1,500 toothpicks. So the most you complete with 1,500 would be the 9th level. Now, if you want to allow partial completion, then you'd need 9 point something. It'd be really close to this, but not quite. And at the 33rd level, you need more toothpicks than we have people on Earth just to do that one level. So, wow. Again, exponential functions grow really, really fast. Now, your exponential functions in general are going to look like this. You know, kind of a basic exponential function would be y equals b to the x, where b is greater than 0 and different than 1. If we had 1 to the x power, that'd be a really boring function. Wouldn't be much of a function at all. It's just be a constant function, because 1 to any power is just going to be 1. Let's start by playing around with an exponential function in the form of compound interest. So your compound interest formula is not something that I make you memorize for an exam, but I would ask that you know how to use it. So let's learn a few things about compound interest. So first of all, we start out with P is the principal. That's not the person who paddled you in kindergarten or whatever. That's how much you invest initially. T is time. R is your rate of interest as a decimal. So for instance, if you're getting 2.3%, actually you should probably get something better than that. So I think SoFi Bank has some pretty good interest rates. Last time I remember looking up, there was 4.3% interest on their bank accounts. Now, you have to rewrite that as a decimal. If you leave it as 4.3 and put it in this formula, you're really telling your formula that you have 430% interest. If you have a place where you can get 430% interest and it's legitimate, share it with me and I'll give you extra credit. All right.
Share it with me.
Yeah, share it with everybody. All right, but you have to write that as a decimal. So 0.043. Make sure you move that 2 places to the left. And finally, n is the number of times of year that interest is compounded. Now, for myself, I always thought there was 365 days in a year, but when bankers calculate interest compounded daily, they use 360. No joke, they use 360. Doesn't make a big difference. I think this goes back to the days when we didn't have all the nice technology that we do now, and it was just harder to calculate with 365 as opposed to 360. Doesn't make a big difference. Even if you're Bill Gates, you wouldn't notice a huge difference in your account using one versus the other. Let's see what we can do here with this one. So if we have $3,000 invested at 8% interest compounded quarterly, now this compounded quarterly is telling you something about how often interest is invested. How often do you think interest is going to be invested if you're compounding quarterly? 4 times a year. Then you'd have monthly for 12, daily is 360. Continuous is not something we're going to do just yet. That's going to be T equals 4 years. That's your principal, 3,000. And I think we've got pretty much everything we need. And rate of interest. What should I put in for R?
0.08.
Yeah, thank you, 0.08. So let's fill in our formula. Like I said, I will give you the formula on the exam. There's 2 things I'm going to expect from you. One is that you show me how to fill it in. So A equals P times 1 plus R over N to the NT. That's going to be 3,000. 1 plus 0.08 divided by 4 raised to the 4 times, that's not good. I won't do that on a test. I want to see the different numbers. So I'd probably use 5 or 6 years or something like that so you don't have this 4 and 4. But that's what we get for this one. That's okay. The second thing is I want you to calculate this number and round it appropriately. So take out your calculators. Let's clear out of here. The trick in doing this is just to type it in once without hitting the enter key. So I'll start with a 3,000 and a left parenthesis. Your calculator understands that if you write that number next to this, that it's being multiplied, so you don't have to put a times in there. If you want to, if it makes you feel better, go ahead. 1 plus 0.08 divided by 4, parenthesis, don't hit the enter key just yet, raised to the exponent. So raised to the power of 4 times 4. Now, depending on you and your calculator, maybe you just want to put in raised to the 16th power. That would work fine. But sometimes this product here is more than you want to do in your head, so nice. So we get 4,118.357. Let's write that down. 4,118.357. Where should I round that off? What does it make sense to round this off to?
The second decimal.
Yeah, the second decimal, because that's pennies, right? We don't have any, in fact, that's changing, right? We're not.
In Canada,
A moment of silence for our pennies, because
they cost
gonna-
more to make than they are.
they cost like 3 cents to make, I think. So yeah, the penny I think is going away. A
Hopefully.
moment of silence. All right,
Like
but
Canada.
I do expect that you're going to round this to the nearest hundredth. Okay, it's money, so, and I will try and remind you subtly, but the final answer for this should be $4,118.36. So that would be our answer for something like that. So hopefully this is an easy problem for you. Just a matter of filling in. The one thing you got to be careful of, like I said, is making sure you change this to a decimal. Let's do a little thought experiment and see what happens if we forgot to change that to a decimal. So let me go back here and delete the decimal and put in an 8 and see what happens there. 1.2914, etc. E11. Does anyone know what that E11 all means?
10 to the 11th times.
So it's times 10 to the 11th. So that'd be like about $129 billion. If I could get $129 billion out of my 3-year or a $3,000 investment, I think I'd be retired. I know it would be. I'd be retired and own an island here or someplace, you know. So if you're getting these huge numbers and they don't make sense, maybe stop and think. You know, you're not going to get super wealthy investing at 4% or 8% interest.
What would
It's
you do
nice.
If you forgot the 0 and you did 0.8 then?
If you did 0.8, you'd probably get something that, well, it's not going to be as dramatic if you actually accidentally put it in the wrong spot for the decimal. I mean, it still sounds really nice, but it might be enough to arouse your suspicion going, wait a minute, that's a lot of money to make after just 4 years. Yeah. So, all right. In any case, let's think about exponential functions in general. And I think I put a link on D2L to this page here, right here. So let's look at various exponential functions. And it wants us to understand and appreciate a few of the features of an exponential function. So I've got several exponential functions here. Let me kind of shut them off and turn them on one at a time. So here's the graph of 2 to the x. And then let me turn on the graph of 3 to the x. Then 4 to the x. What's happening is I increase the value of the base here. 2, 3, 4. What do you expect to happen when I look at the graph of y equals 6 to the x?
It's going to be even less on the x-axis.
Okay.
Skinny.
But all right, so it's going to be kind of skinnier. It's basically going to be taller, stretched away from the x-axis more. So there you go. You can kind of play around with this if you'd like. You can turn this on and then highlight, you know, each of the graphs one at a time. So, you know, look at 2 to the x, 3 to the x, 4 to the x, 6 to the x, etc. But all these graphs have a few features in common. So one of those features is this. The graph passes through the point 0, 1. that's kind of what I regard as the vertex of this graph. I mean, it's not the right term to use for that, vertex, but it is kind of close. But it's a point that I like to see on your graphs. Now, there's a couple other things that are happening with these graphs. One of them is that the graphs grow exponentially. They take off. They grow really, really fast. You saw that when you did your work on your handout. Take a look to the left of the x-axis. What's happening to the left of the x-axis? Yeah, they're getting really, really close to this dotted line down here, y equals 0. All these graphs are getting very close to that value. So that value is, this line here is an asymptote. So let's write down a few things about this graph. One is that it passes through the point 0, 0, or excuse me, 0, 1. Hate when I do that. 0, 1. Yeah. Second, and this is for values of b that are greater than 1, it grows exponentially. It takes off. And that's what you could have seen or concluded on our handout here, is that you're getting exponential growth. The graph just skyrockets. And the last thing, for x less than 0, the graph approaches y equals 0. It's a horizontal asymptote. It gets close to but never quite touches that point. So, all right, interesting. Let's play around with an example in the form of number c and just kind of get used to the form and the shape of this graph, 2 to the x. So I'll give you a couple more seconds to copy those down, and then we'll move on to example C here. So let's move down here to example C. We've got some exponential functions. Let's see if we can't match them up with the graphs. So for instance, this one right here, y equals 2 to the x. Which of these 4 graphs looks like a winner? Which one of these 4 graphs looks like y equals 2 to the x?
The third one.
Yeah, the third one. Thank you. So there you go. You got a nice increasing function. It passes through the point 0, 1. It gets close to, but never quite touches the x-axis. Now, how about this one over here? Y equals 2 to the negative x. So we replaced x by negative x. Now, that can do really a couple things. Does it flip it around the x-axis, or does it flip it around the y-axis? What do you think is going to happen there? Yeah, it's going to flip it around the y-axis. So which one of these graphs looks like it's been flipped around the y-axis? Yeah, the first one. Okay, so that's the first one. Before I look at this next one, let me play around with this one. So I'm going to come over here to the right and look at y equals 2 to the negative x. And I'm going to rewrite this. How about if I rewrite this as y equals 2 to the negative first power, then raised to the x? Are those the same thing?
Yes.
Michael says yes, he's right. Somebody tell me why he's right. Why is he right? What do these exponents do when you remove the parentheses? They multiply. Negative 1 times x is negative x. So they are the same. Is there another way I can write 2 to the negative first power? Yeah. 1 over 2 to the positive first power. Okay, cool. So what's that saying about this next graph? About this next equation? Y equals 1/2 to the x. Saying that it's the same as this one, right? So I'm getting double duty out of that one because it's the same there. Now, let's start out with this one and compare this one to this one over here. What change do I make in going from this graph to this one over here?
The negative,
The negative. What effect is that going to have on my graph?
the way it faces.
What's it going to do to the graph? See? Ah, well done. It's going to reflect over the x-axis. So which one reflected this graph over the x-axis? Which one looks like that one? 4. So there you go. Nice. Nice. Let's continue to play around with some of our graphs here and see how they've been changed and reflected. Yes, sir.
What would a problem look like for number 2?
Oh, for this one?
Yeah.
That's a great question. What would this one? Take a look at one of your graphs. Can you relate this to one of your other graphs?
Looks like 4, but
Looks like 4, but flipped around the y-axis. So we could do that.
Or it's 3 reflected across the x-axis.
3 reflected across the x-axis. What would reflect the graph of 3 across the x-axis? What do we got to do to flip it upside down like that? Yeah, put the negative in front of the 2. So this would be y equals negative of 2 to the x. That would be that graph there. So great question. Appreciate that a lot. Now, we're going to play around with some more graphs and try and figure out how some of these have been shifted. So we're going to compare these equations. We're going to start with y equals 3 to the x. How about y equals 3 to the x minus 4? How is that going to compare to the graph of y equals 3 to the x? It shouldn't be drastically different, shouldn't it? So let me shut off these and this as well. Let's move down to let's see, example D here. I thought I had it set up differently. All right, let's just do this. So we've got y equals 3 to the x, and this time I want to do y equals 3 to the x minus 4. What do you think that minus 4 is going to do? How is it going to shift my graph? Left, right, up, or down? So the one point that I want to keep track of typically is this one here, 0, 1. And I want to see where that's going to be in my new graph. So let's understand why I get this point. I get that point because 3 to the 0 power is 1.
For the worksheet that we did, if you put in 0, you end up getting 1.5. You don't get 1
Where?
for the worksheet.
But where are you putting in 0?
Like if you plug in 0 to our equation, 3 times 2 and minus 1.
Oh, if you plug in a 0 here?
No, not into that one, the 2 picks.
Yeah, but we don't have a 0th level.
Right. Okay.
Yeah. So I appreciate that, but we didn't have a 0th level. So the question is, what would make this exponent equal to 0?
4.
A 4. So that means that if I put in a 4 for x, I should get a 1 for y. 4, 1. So that should be my new point. So it looks like it's been shifted how? Looks like it's been shifted to the right by 4. Oh, okay. Well, that's cool. So that one got shifted to the right by 4. All right, right by 4. How about if I put a negative in the exponent? 3 to the negative x. What's going to happen with that one?
It'll approach 0.
In which direction?
Positive x.
What's that negative going to do to our graph?
The Y.
Yeah, thank you. Flipped around the y-axis. So you are right, Michael. It is going to approach y equals 0. 3 raised to the negative x. It's just that it does that kind of opposite of what our original function was. As you move out towards positive infinity, this graph gets smaller and smaller and smaller. Whereas our original graph, 3 to the x, the graph got bigger and bigger and bigger. But they're just mirror images of each other around the line y equals x. All right, well done. How about over here? What's going to go on with this one? What's that going to do to our graph? Flip it around the x-axis. Good. So flipped around the x-axis. Now you start getting into combinations of things. So in this case, let's take a look. What's the plus 5 going to do to the graph?
Oh, left.
Left by 5. And reflected how, Heba? Around the x-axis. Reflected around the x-axis. Nice. And kind of a double shift on this next one. Reflected around, no, not reflected around, but shifted how? What else we got that one? Elizabeth, how would this one be shifted?
It would be down 5 and to the left 2.
Yep, left 2, down 5. Nice, nice. So let's take a look at this last one kind of slowly, and I think I do have the graph for this one put up here. Back here. No, not quite. All right. So let's take a look at things one at a time for the last one. So we'll start out with y equals 3 to the x minus 4 and see what happens there. So y equals 3 to the x minus 4. And that should be pretty predictable. With decimals, you got to put parentheses here. It won't let you just automatically stay in there. So I shifted to the right by 4. All right, nice. How about y equals 3 to the x minus 4 and then plus 2? Now what's going to happen with that plus 2? Up 2. So the point that was at 0, 1 got shifted to 4 and 1, and then you're going to add 2, so it should be up here. So you should have a point at 4 and 3. Those are the points I generally like you to keep track of for your graphs. Let's look at one more thing. What if I flip this around the x-axis? Now what takes priority? Multiplication or addition? What am I going to do first? Multiplication. Remember, please excuse my dear Aunt Sally. You do parentheses, exponents, multiplication and division before addition and subtraction. So y equals negative of 3 raised to the x minus 4. So that's shifting it over and flipping it down. And then the last thing to do is shift it up, plus 2. So there's our final graph. So it's been reflected around the x-axis, shifted to the right by 4, and up by 2. Notice that this line right here, this number right here, is always going to be your horizontal asymptote. So in both of these graphs, let me get rid of this one here. In both of these graphs, the line y equals 2 is a horizontal asymptote. The graph gets close to, but never quite touches, this horizontal line. So that horizontal line is a feature that I often look for seeing on your graph. So reflected around the x-axis, around the x-axis, right by 4, and up by 2. A different way I could ask you these questions is I could say, all right, take this graph and shift it to the right by 7, up by 4, and reflect it around the x or y axis. So I could tell you what I want shifted and then ask you to come up with the equation. Are we okay with that one? Let's zoom in on this. And I think the reason I have this one graphed is because I wanted to look at the domain and range. To remind you of domain and range, so that way when you get to calculus, you're not mad at me like, hey, wait a minute, he didn't tell us about domain and range. So let's make our function there. Let's turn on that one. So this one's been shifted to the right by 4, reflected around the x-axis, and then shifted up by 2. As far as the domain is concerned, the domain is just your x values. Let's see. So it's your x values. This graph, even though it's trending down towards negative infinity pretty steeply, it does eventually get out towards positive infinity in the x direction and negative infinity in the other x direction. So its domain is negative infinity to infinity. What's the alternative notation I have for this? Script R. But how about the range? The range is your y values, and the y values are definitely kind of limited. Let's look back at our graph. This is one that I definitely would expect you to answer by looking at your graph. The y values start at negative infinity. That's the lowest that they're going to get. But what do they top out at? 2. Do you think it ever actually gets to 2? No. Now decimals might show a 2 there, but that's because it's rounding and getting really close to 2. But it actually never quite gets to 2. So the range should be negative infinity to 2, brackets or parenthesis on that? Parenthesis. Nice. One of the problems you might see at home would be to calculate compound interest with different time periods, 2, 3, 4, 5, 6 years. What I would suggest you do at home is you put this into your calculator this way. You put it in as a function of t, but instead of a t, you're going to use an x. Now our principal was 6,000, so it's going to be 6,001 plus our interest rate. What should I put in for R? 0.07 divided by compounded monthly, n equals 12, raised to the 12 times t, but instead of a t, use an x. If you plug this formula into your y equals key, then you can just use the table to get all the values that you need. You don't have to keep on doing this again and again and again. Do be careful to round this to the appropriate decimal. This is not the only place you're going to see exponential functions. Populations grow exponentially. You'll see this especially like bacteria. I mean, how many times have you gone to bed feeling okay and you woke up and you're like, oh, I don't feel so good. All right, that's because bacteria can grow exponentially, at least for a while. At some point, they're going to run into a problem because there's not enough, room to keep on growing that way. But a bacteria contains 1,400 bacteria initially and doubles every hour. So we saw this when we started out with our toothpick challenge. What did that 3 represent? That 3 represented our initial amount, right? So it was, let's see, we'll call it N of T, number of bacteria depending on time, starts out with 400 and then times 2 to a power. Now unlike here, well, let's see, 2 to the, let's see, is it going to be T? I'm trying to think if I need the minus 1 there. I don't think I do. No, I do need the minus 1. T minus 1. Because at time, do I need it or no? No, I don't need it. No, I don't need it. So that's just going to be a 0. 1,400 times 2 to the T. Because at time equals 0, when this thing starts, what's 2 to the 0 power going to be? 2 to the 0 would be 1 times 1,400 would give you 1,400. At n equal 1, you're going to get 1,400 times 2 to the first power, or 2,800. And then 2 to the second power is going to be 4, and so you're going to keep on quadrupling that. That's going to be 5,600, etc. So there's the formula for how these things double. And it's an exponentially growing formula. Are you pretty comfortable with your graphs or your graphing calculator? Now, a nice way to decide which one of these graphs is correct is by just plugging in some points and plotting them. Let's plug in this equation into our calculator and see if we can't determine, just based on the points we get, which one of these is correct. So I want 2 times 1/4 to the x power. So 2, and then 0.25, there's my 1/4, raised to the x power. I hope you have your calculator set up correctly. In terms of the table, should look like this, with ask and auto set on your independent and dependent respectively. Let's plug in some values. We want g of -3, 128. G of -1, G of 0, G of 1, and G of 2. Okay, so the values that we're getting from left to right would be 128, 8, 2, 1/2, and 1/8. Okay. Now I guess I would look at these and say, oh, well, one of these stands out as being the correct one. You can kind of look at these and say, all right, at -2 I should get something around -128.
It's 32.
Or negative, are you getting -30?
You put in
Oh, negative, oh, I put in -3. All right, so -2, my bad, should be 32?
Yes.
Okay. Well, I'm getting a negative value here, right? So that means this isn't right. If I put in -2 and look for -32, I'm not seeing that one. How about this one? Is that one looking possible? -2, and yeah, something up in the 30s. Okay. And you can check out things on the right side of the y-axis. At x equal 1, yeah, something pretty small, and x equal 2, something even smaller, so that one's looking pretty good. Let's jump on down to, let's see, example I and J. Mhm. Mm. If I was looking at this one, I'd probably rewrite it a little bit. Personally, I like the exponential part in front. So now I know that, all right, here's my exponential function. It eventually gets shifted up by 4. I could probably do a couple other things here. For instance, 1/10 can be thought of as 10 to the negative first power. And then, all right, then that's negative 10 to the negative x power plus 4. And now I can start to see all these shifts coming into play. Let's remind ourselves of what some of these shifts are. What's the negative going to do as far as a shift is concerned?
Flip.
Across the,
Yeah. Flip across the x-axis. How about up here? What's that negative going to do? Bless you. It's going to make you sneeze. Flip around the y-axis. And then what's that last plus 4 going to do? Shift up by 4.
Wouldn't that plus 1 also be our asymptote?
Yes, the 4 is going to be your asymptote. In fact, I do believe that I put that here on your graph for you, right here. Because that y equals 4 is going to be your horizontal asymptote. Now keep in mind, you're not going to be taking your exams without a graphing calculator, although there is some mumbling about that because there's a lot of colleges and universities that are moving in that direction. I'm not sure I really agree with that. But for us, we're not going to make any changes in that direction in the near future, for sure. So let me graph this. Negative 10 raised to the negative x. Move to the right one to get out of the exponent, plus 4. As far as the window is concerned, if you're looking at it going, I have no idea where to graph this, you don't have to think too hard. Just borrow the dimensions of the graph that I've given you here. All right, so let's zoom in a little bit. So negative 1 to 6 in the x-axis and negative 0.5 to 5 in the y direction. Negative 1 to 6. And let's make a scale of 1. Negative 0.5 to 5 in the y direction, and again a scale of 1. Okay, there's your graph. And as a bonus, we can see the y-intercept. Nice. It'll be a problem for later when we talk about logarithms to find the x-intercept. Alright, so something x and y-intercepts, yeah, I'd like to see those graphs, especially when the numbers are easy. I'd like to see those graphs reasonably well, if you don't mind, please. Now, if your graph accidentally touches this, that's fine. Just don't egregiously go through it and then bounce back. Just try and stay on the one side of that. Okay. Last but not least, let's try and build another mathematical model for some exponential growth. This would be for the number of yeast cells in a freshly brewed batch of beer. So when you brew, you have to cool down your wort and then pitch your yeast cells. So initially, one of the vials that a friend of mine has told me about has 120 million bacteria to begin with. And let's say it doubles every hour. So it's going to be times 2 to the x power. Maybe I should put a t here, but n of x. So wow. How many of these guys are there going to be after 24 hours, assuming that the growth is unlimited? Now, the one thing I want you to see here is that you're going to get a number that's big enough that you're going to have to put it in scientific notation, or that your calculator will put it in scientific notation. So 120 million times 2 raised to the 24th power, and bam. So, wow. I'm thinking that they're going to run out of food before they get to that level. But if this level continued, unabated, then this is how many bacteria or yeast cells you would have. 2.013 times 10 to the 15th. 2.013 times 10 to the 15th. Now, let's see if we can't write that in regular decimal notation. So it's going to be a 2. Is this going to be a really big number or a really small number?
Big.
Where should I move the decimal? To the right or to the left? To the right. To make it a big number, you want to move it to the right. So once I move it past these three, 0, 1, 3, I've got 12 more spaces to go. So, wow. Lots of happy yeast cells, assuming they get better. Nikki, is that a question or just?
No, just-
Gotcha. Okay. All right, cool. Comments or thoughts? All righty.
How might you graph a population that stabilizes?
So that would probably be more of a logistic function. I think a graph like that, let me just go over and borrow some of these. Let's do it this way. New blank. I think that would be the log of, let's see, y equals log of x over 1 minus x. So, yeah, I gotta have that turned upside down. Let me just do it this way: x, y, and y. So something like that. So you have an initial growth, but then it'll stabilize and reach a maximum.
Oh shit, okay.
So, yeah,
That S-curve is fascinating.
yep, cool stuff. I gotta look back at the exponential or logistic functions, but that's generally the shape.
That means that you can model...
Yeah, you can model lots of stuff.
That, yes.